Hello chemists, this is Ms. Placino and you're watching lesson 8.2 on decay equations. In today's lesson, we're going to cover how to represent nuclear decays as equations. Goals for today's lesson include being able to classify a decay as being alpha, beta, gamma, positron, or electron capture. If you're not familiar with what those terms mean, go back to lesson 8.1 and review. You're going to be able to balance nuclear decay equations and write complete decay equations for a radioisotope. So lots of stuff to do today. Let's go ahead and get started. Anytime we have a nuclear decay, whether it is something like a natural transmutation, what we talked about in the previous lesson, or something like an artificial transmutation, which we'll talk about in future lessons, it's all about conserving mass and charge. Basically for us, this means that the mass number and the number of protons has to be the same on both sides of the equation. If you'll remember from the previous lesson, if you've got the configuration of an isotope looking like this, the U, of course, stands for uranium. It's these numbers that we're concerned with. The 238, remember, is the atomic mass. And in this case, the 92 is the atomic number. So when we go to write equations, we need to make sure that that top number, the atomic mass, is the same on both sides of the equation, and the bottom number, the atomic number, or the total charge, is the same on both sides of the equation as well. Nuclear reactions are going to deal with changes that occur in the nucleus. We are going to ignore electrons. The issue with electrons kind of gets sorted out naturally on its own. We don't have to worry about, oh, well, we had an alpha decay occur and we lost 2 protons. We have those 2 extra electrons still hanging out. Is that going to make an ion instead of an atom? No. Don't make it more complicated than it needs to be. We are really just focusing on the nucleus. Again, completely ignore the electrons. So we're going to take our radioactive nucleus and we're going to be able to predict whether alpha, beta, or gamma decay would occur. We did talk a little bit about that in the previous lesson. And now we're just going to be able to represent those changes with a balanced nuclear equation. So we're going to dive right into some practice problems. All right, so let's look at a couple of questions over in 8.2. And question number 1 is asking you to solve for the missing decay particle and classify the type of natural transmutation that is occurring. So let's take a look at the first problem. So we've got an isotope of copper decaying to become an isotope of nickel and plus some unknown particle. All right, so when we go to attack questions like this, really we've got 3 different steps. First, we're going to take a look at the masses. On the reactant side of the equation, I see a mass of 58. On the product side, I also have a mass of 58. Therefore, what does the mass of X have to be? Yeah, I can't have any mass at all. If I gave it a mass, it's going to kind of unbalance my masses. We'll do the same thing for the number of protons or the charge. I've got 29 on the reactant side. I only have 28 on the product side. So what must be the charge or number of protons present in our unknown particle, X? Let's see. 28 plus 1 would give me 29. Now I'm balanced. You might have to check reference table O to figure out kind of what notation, what symbol would go there. I've got something with no mass and a charge of plus 1. Yeah, this sounds like a positron. So whether you'd like to represent that with the E, or if you prefer that's valid as well. I'm going to leave it as just the like positively charged electron. There we go. Yeah, so my unknown particle, X, is a positron. Since a positron is being produced, what type of decay is undergoing? Yeah, this should be positron decay. And that's really all there is to it. Let's try another one. We'll go through, let's do A, B, and C. Why not? So I'm going to check my masses. I'm already balanced on both sides of the equation. So I must have no mass. I've got 93 protons on the reactant side. 94 on the products. So must have a -1 because 94 minus 1 equals 93. Now I'm balanced for charge or number of protons. Again, I'm going to see E as my symbol. Looks like an electron is being produced when we're talking about nuclear changes. Remember, that's a beta particle, making this beta decay. Try out letter C. A little bit different since we put the X on the other side of the equation. I must have the same mass, 168, because 0 plus what equals 168. I've got 68. I got a -1 on this side, so that must be a 69. Oh, how can I figure out the symbol of this particle? Hopefully you're thinking, well, we've got 69 protons in its nucleus. Let's use the periodic table and find element 69. So if we check the periodic table, we find element number 69. Oh, here it is down here. Element 69 is Tm, or thulium. Definitely one we don't come across very frequently at this level of chemistry. So I can go ahead and include that as the atomic symbol. That is one of the things that can be kind of tricky when people are first learning how to do this. Remember, that number at the bottom, the atomic number or number of protons, will help you figure out what the symbol is supposed to be. What sort of decay has undergone here? I guess has X undergone here, to be more specific. Yeah, this is an electron capture. If you were thinking this is a beta particle or a beta decay because you see that, well, careful. In beta decay, a beta particle is produced. In electron capture, an electron is getting pulled into the nucleus. So electron captures will have multiple reactants, whereas all the other natural transmutations that we studied will just have one reactant. Right. Definitely take some time to try out a couple of more of those and make sure you've got the hang of this. Let's make it a little bit more advanced. Let's say you need to write out a complete balanced decay equation. Let's take a look at question 2a. We have thorium-232. Oh, geez. At first glance, it might seem like you don't have enough information to complete these. Yesterday, we talked about how you could go through and use the proton to neutron ratio to try to make a prediction about what sort of decay will occur. But you also have a reference table that's going to be extremely helpful for solving these types of problems. So let's go back into your reference table and find table, I believe it's table N. Yeah, table N. We've got selected radioisotopes. So these are about 24 or so different isotopes that New York State has selected for whatever reason. And if I find thorium-232, we don't have to worry so much about this half-life column just yet. We'll get to that a little bit later this unit. But it tells us what decay mode thorium-232 will experience. It's going to be alpha decay. So let's get back to our problem and see if we can use that information to write a complete balanced nuclear decay equation. All right, so we've got thorium-232. You know it's going to undergo alpha decay. Alpha decay is just a helium nucleus. Whether you want to write that as He or the symbol alpha really doesn't matter to me. Now it's like the previous sets of problems that we were working on. We were trying to find the unknown. What is something we should do to make our life a little bit easier in predicting our product? Yeah, I'm going to want to use the reference table to look up the atomic number of thorium. This unit tends to be really reference table heavy, so you're going to want to have that handy. Thorium. There we have it, element number 90. And it's going to undergo alpha decay. So I apologize, it's a lot of bouncing back and forth between these two. Okay, so if I have a mass of 232 on the reactant side, I need a mass of 232 on the product side. So this must be 228. I've got 90 protons on the reactant side. I already have 2 on the product side. So we must see a number of protons of 88. And again, back to the periodic table, find the element with 88 protons in its nucleus. There we go. It's radium, Ra. And there's your decay equation. Again, use table N so you can figure out the type of decay a radioisotope will undergo. Go ahead and try out question 2b. Write a full decay equation for phosphorus 32, then unpause the video and check your work. Let's walk through this one. So I've got phosphorus 32. So I know the mass is 32. My symbol is P. And using the periodic table, I could look it up and find that phosphorus has an atomic number of 15. We're going to undergo decay. So I'm going to check table N to figure out what sort of decay will occur. Table N says that beta decay occurs. I might need to remind myself what beta decay looks like. You've got table O, the very next table, that tells you the different symbols. Beta decay can be represented as an electron, no mass, and a charge of -1. All right, now I'm just kind of solving for the unknown nucleus. I have a mass of 32 on the reactant side, so I need a mass of 32 on the product side. I've got 15 protons on the reactant side. I have a charge of -1 on the product side. So what plus -1 equals 15? Hopefully I'm not pulling out a calculator for this. We get 16 protons in the nucleus of our unknown element. And again, checking the periodic table, element 16 is sulfur. And that's it. I would dare to say that conceptually this isn't too terribly difficult. Same deal mathematically, this isn't too difficult. Be careful though. Use the reference tables so that you can look up the symbols, you can look up the type of decay that occurs, and be careful with making classifications. As always, keep chipping away at these practice problems so that it feels a little more second nature. And we're going to build on this concept and start looking at some artificial transmutations in a future lesson. Good work today with this, chemists. Thanks for tuning in, and I hope you found this helpful.